Amry, MRG Laboratories, Delta P Reliability Services, and Fifth Order Industry. Not industries yet, but right now just a single industry. In a moment, we're going to get started with Mike Johnson of Amry. Mike's going to talk about the lubrication management and the challenges thereof in the time of this COVID-19. Okay, looks like to be 10 o'clock right now, Central Standard Time, 11 o'clock Eastern, and God only knows what time it is where you're at. But I do want to welcome you to join the Lubrication Reliability in the time of COVID-19. Sponsored by Amry, MRG Laboratories, Delta P Reliability Services, and Fifth Order Industry. My name is Mike Holloway. I have the pleasure to introduce Mike Johnson of Amry today. He's going to talk about the lubrication management and the challenges thereof for the next 59 minutes or so. So without any further ado, I'll turn this over to Mike and have at it, Michael. Thank you.
Thank you, Mr. Holloway. Very much appreciate the introduction. Welcome to everybody. It's great to have you here. We're all hopeful that during the course of the next 4 sessions and our wrap up on Friday, that each of you will find something that serves you well at your facility during this time of difficulty around the virus that is circulating the globe. I'm going to turn off my camera here and starting with title, the topic of my discussion is managing a machine lubrication program in the time of COVID-19. A little bit about me, 33 plus years involved in helping customers improve mechanical reliability through the work of essential care and machine lubrication. I've been fortunate to speak in a lot of different events and produce content that's suitable for instruction to folks that are working in this area to improve mechanical reliability. I've noticed during the review of registration some common themes in our multiple points of interest here. Several shared points of interest, knowing where and how to safely reduce scheduled activities, figuring out how to maintain service coverage with fewer available hours from the social distancing policies that we are all enduring, making sure that the practices that we have, that we are executing, still reflect something that represents best practice. Understanding how to properly idle machines so that they're ready to operate in the future, whether that be a short-term or long-term. They're free and safe from corrosion during idle time. And then the last common theme I saw in the registrations was seeking to understand how to improve practices, not just prevent the decay of machines. So I will kind of focus in on those shared themes. The bottom line, during this period of uncertainty, we all face having to get the work that we have done with fewer resources than we're accustomed to having. We all know that the machine lubrication effectiveness plays a substantial role in preserving and protecting machine productivity and plant productivity. And the content we will each provide is focused on showing everyone how, to the best of your ability, you might go about preserving, protecting your production machinery through precision work practices. In this session, we're going to cover 3 topics: optimizing intervals to safely extend visits and protect machine surfaces, putting machines into an idle state without increasing risk of deterioration, either short-term or long-term. And then lastly, as we plan ahead for the future, giving you some ideas that you might consider for long-term storage, lubricant storage and handling improvement. Of course, we're going to start with this topic about extending service intervals. Service intervals are labor-consuming elements, and we need to find a way to do our work more efficiently. Now, before I dig into the topic, let me just hit on a couple high-level background ideas. It has been said that our industrial world rides on a 10-micron oil film. The reality is, for our element bearings and our plane bearings, it's nowhere near 10 microns. It's somewhere between 1/2 and a comfortable 3 to 5 microns for plain bearings. The reality we face every day is that our industrial livelihood, wherever we may be running, floats on an oil film that's the thickness of a red blood cell. Now, we know from looking at statistics provided by component manufacturers, bearing manufacturers in this instance, there's a substantial relationship between the effectiveness and the life cycle of our lubricated machine parts and what we're doing with and within machine lubrication. Per SKF bearings and research they've conducted, 57% of the instances of premature bearing failure fall at the feet of machine lubrication. FAG Bearing has done similar research, and per their understanding, it's closer to being 80% of premature bearing failures related to some issue involved with machine lubrication. So it is to our benefit for us all to focus on what we may do to the best of our ability to provide a continuous coating of oil that cushions and seals our lubricated machine parts, preventing surface contact and preventing surface degradation due to exposure to the elements. We don't find a way to maintain that uniformly consistent, clean, dry, red blood cell thick protection film. We are sure to experience wear from surface rubbing, from contamination, from fatigue, from corrosion, all of which leads to the loss of machine working parts, the loss of production time from scheduled or unscheduled repairs, the loss of machine repeatability, increased risk of injury, higher production cost per ton of whatever it is, or per unit of whatever it is we're trying to produce, all of which leads to a less competitive position. So all of those failure modes are measurable, predictable, and avoidable. Now, with that in mind, let's dig into our content. Bottom line is, during this time of social distancing and in our respective countries trying desperately to protect ourselves from the scourge that is circulating the globe, we find ourselves on split shifts without enough people to handle the normal workload that we are accustomed to trying to handle. To that end, we need to find some ways to optimize the service intervals for our machines. So we think about what our most time-consuming service intervals are. We find that they're level check and top-ups. But let me see. I'm going to back up one page here. Yeah, sorry about that. Safely reducing the labor burden means we need to focus on the machine sump, level checks and top-ups, and grease replenishment activities. Okay, here we are. So the level checks and top-ups. This is an easy solution where we have tightly sealed sumps and reservoirs where there is no leakage. We should look to double the normal service intervals for the care and feeding of our machines. I would propose that we not go beyond a month because a lot of things can happen within 1 month. But if we're currently experiencing daily to weekly service intervals, we can safely extend those as long as the machine is not leaking. And of course, once we identify any instance of leakage, we should shorten that back to our starting point, or at least shorten as needed. For the leaking sumps and reservoirs, maintain the existing frequencies and focus on correcting leaks if possible, under the assumption that something in the neighborhood of 80% of our existing leaks are controllable once we begin to focus upon them. That's kind of the easy part. Oil service intervals can easily be extended. Grease replenishment replacement intervals is a little bit more difficult. Grease replenishment intervals are determined by the components, let's say bearings, the bearing size and type, operating speed, and environmental and production operating conditions that bearing operates in. All of these things influence grease health, which Rich will get into in some detail in an upcoming session. So we have to kind of right size our grease replenishment intervals based upon the operating conditions. And I'm going to start with an example of an electric motor. It's very common practice in industry to take the old standby. We lubricate motors every 6 months or a year. If it's a vertical shaft, perhaps we lubricate at 3 to 6 months. And we use kind of a nominal value, 1 shot, whatever that may mean, of grease per each 25 millimeters of shaft diameter. Well, this is a poor design based upon a crude understanding of grease failure modes. It's either too much or too little, and in many instances, substantial amount of wasted time. So I'm going to run you through some logic that we can find, starting with the nameplate information for the motor and the use of a simple radial calculator that's available for you to right size your grease feed practices with the expectation that you're likely to find a substantial amount of time savings available through these means. If you go to your motor nameplate, you will find details that look like we see here. And we see in the red boxes 60 BCO3 and 50 BCO3. This is the Anti-Friction Bearing Manufacturers Association code for identifying the bearings that are used within the machine. The larger number is almost always representative of the bearing close to the coupling. The smaller number is the opposite side. In this instance, 60 represents the bore diameter in millimeters for the drive-in side or the opposite side. BCO represents the bearing that's identified, Conradson ball bearing, and 03 represents the bearing series or bearing grade. Here's another example, a different motor nameplate using similar naming structure with a few extra details. Now, within this naming structure, we see all the information that we need to find to calculate and optimize our grease replenishment activities. 45 and 35 are the bore dimensions. BCO, once again, is bearing type. 03 is the bearing series. And we have information about cages, metal shields, and internal clearances. A note about the difference between a shielded and a sealed bearing. Shielded bearings are intended to be replenished. This must be done slowly and very carefully. And if we don't do this properly, if we don't have the right technique, we can actually damage the bearing itself. Sealed bearings are not supposed to be replenished at all. They should have a 2 to 4 year service life, which is largely a function of the quality of grease used by the bearing manufacturer. We typically find these on smaller motors, smaller bearings, at lower shaft speeds. Where we see a shielded bearing, we need to know that we should proceed very carefully. There's also another very common naming structure or standard, the ISO or DIN code, which we see noted here. A similar numbering structure, the last 2 digits in this series, 08, times, when multiplied by 5, gives us the bore dimension. The first 2 digits in the series, 63 or 62, points us to the bearing type in series. The UU in this instance suggests 2 bearings face mounted against each other. Here's another example of that. In this instance, we have 6310 on the load side and the same size bearing on the opposite side. We have the motor speed, 1165. For both bearings, the first digit, 6, designates a deep groove ball bearing. Second digit, 3, designates the gauge of the bearing. The last 2 digits, when multiplied by 5, gives us the bore dimension in millimeters. So let's use this information to solve a problem here. Well, here's another example, just so you see how it's represented by various motor manufacturers. It's the same code structure and the same representation. So using that information, we're going to take a simple radial calculator and calculate the frequency, volume, and make a decision whether or not the product that we have in place and frequency have in place is a good fit. There's 3 calculators in the set. The blue calculator is for ball bearings, the gray is for cylindrical bearings, and the orange calculator is for double row spherical roller bearings. So we certainly have to use a calculator that's appropriate to the bearing that's found within the machine. So here's an example of that 6310 C3 nameplate. 6 designates that it's a ball bearing, so we use the ball bearing calculator. The last 2 digits, 10 times 5, designates that it's a 50 millimeter bore. So we go to the calculator, we turn to the place on the dial that says 50 millimeter bore. From here, we can see that at regular, normal or designated operating speed, which rounds to 1200 RPM, the viscosity that must be provided by the grease in order to make the elements float is 20 centistokes. Ideally, we would like that to be 3 times that value, or rounded down to 59 centistokes. Further, based upon operating conditions where we have dry, clean, low to moderate temperature, low vibration, we see the calculated replenishment interval. This value is based on a DIN standard that is provided to us by design engineers working in conjunction through SKF and FAG bearings back in the 80s. Also, we see from the calculator, if it's a 6200 series bearing with a 50 millimeter bore, the volume is 9 grams or 0.3 ounces. If it's a 6300 series, which happens to be the case in this instance, we're looking at 14.9 grams or 0.5 ounces. And this is a instruction to us that we should put no more than that quantity of grease into the bearing cavity. Further, on the back side of this calculator, we can validate that the product that is in use is the correct product or the best fit product. We know that we needed to have at least 20 centistoke and preferably 50 centistoke from the viscosity of the lubricant used to care for the bearing. Let's say we have a 60 degrees C operating temperature, and this diagonal line here with the number 100 above it represents the thickness of the oil that is used to make the grease. Well, at 60 degrees C, an ISO 100 oil, the deflection point, shows us that we are actually operating with 40 centistoke of viscosity. We needed 20. We wanted to be around 50. At our current operating speed, we're setting at 40. The product in place, a typical electric motor grease under these conditions, would be considered to be an excellent fit for the long-term care and health of the bearing. We're going to run through this one more time using another scenario. In this instance, off of the nameplate, we see the 6313 bearing designation. 6, once again, represents ball bearing. 3 represents the gauge of the bearing. And 13 represents the value when multiplied by 5, gives us the bore dimension in millimeters. We turn to the 65 millimeter value on the calculator. Now we see at 1500 or 1495 RPM rounded up, this bearing, slightly larger bearing, turning at a slightly higher speed, requires 15 centistoke. Ideally would like to be floating on oil that's 44 centistoke at operating temperature. And based upon the operating conditions, and let's say we have high humidity, moderately high temperature, and low vibration, would have a shorter replenishment interval. Once again, we can use the values on the backside of the calculator to determine whether or not the grease is a proper fit. In this instance, if we were using a general purpose grease that was made from an ISO 220 viscosity grade, we see the diagonal line for the 220 here. If the bearing is operating at 50 degrees C and we're using an ISO 220, that gives us 110 centistoke. Well, this kind of shows us why general purpose greases are not a good fit for electric motors. Based upon the size and speed with which the shaft is turning, this bearing wants no less than 15 centistoke, but preferably 44 centistoke viscosity from the grease. If we're using a general purpose grease, like we see here, we would have 110 centistoke, which is way too thick to satisfy appropriate lubrication requirements for the bearing in the motor. In this instance, the grease would be a poor fit and could produce a problem called channeling, which will lead to starvation and failure. We could have a bearing housing full of the wrong kind of grease, and the bearing could starve to death because the grease is not able, the oil in the grease is not able to provide adequate coverage. So it's vitally important, not only that we determine the frequency, went the wrong way, excuse me. We determine the frequency, 113 days for high humidity, low solids, moderately high temperature, low vibration, volume, but then also that we validate that the grease that is in use is the appropriate product to service the bearing's requirements. Here's an example of applying this kind of calculator to a tail pulley bearing. Now, in many instances, our slow turning bearing intervals could be extended very safely and to quite a much longer interval with the right information. Let's say hypothetically that the bearing inside this housing is a 222-15. 222 represents that it's a double row spherical bearing like we see here. So that would be the orange calculator. The first 3 digits designates the bearing type and gauge. The last 2 digits, once again, when multiplied by 5, gives us a bore dimension for this bearing. So 222-15 is a 75 millimeter bore. We turn our dial indicator to the location that gives us 75 millimeters. We estimate machine speed, and for a tail pulley shaft on an apparatus like we're looking at, we can actually watch the rotation and determine what that is. But the lowest interval in the calculator gives us 100 RPM. Well, this bearing, turning at 100 RPM, requires a viscosity of 95 centistoke at operating temperature, and ideally would be 3 times that value. We see down here for the 222 series, we have a grease replenishment value. So we have all the information we need to establish an interval, identify that the product type is a good fit, and establish a stopping point for the volume. We turn the calculation over to the back side. We see that if this bearing is operating at 40 degrees C and we're using a general purpose product, that we actually have 220 centistoke for the product, where the bearing is looking for something between 95 and 284 centistoke. So then we find that the general purpose grease for this particular pillow block bearing is actually a very good fit. The product is the right fit. And then now it's just a matter of identifying the operating conditions that are reflected in these gray and white lines to give us a sense of the difficulty of the operating state. If this bearing is operating on a conveyor with high atmospheric solids, high temperature, moderate vibration, then we need a shorter interval. If, on the other hand, the operating environment is dry and clean, and the operating temperatures between 40 and 60 degrees C or 104 or 150 degrees Fahrenheit with low vibration, then we could see how that interval could be very safely justified to be quite a long time frame between trips back with a grease gun to feed this bearing. And then lastly, once again, we have identification of the quantity that's the right quantity to stop when we're feeding the bearing. No more than 0.7 ounces, no more than 20.2 grams. And these values are dictated by the bearings themselves. So with a simple tool, a simple radial calculator printed on cardboard, we can go into our plant site, look at those intervals where we have what we perceive to be kind of a long operating state. Scratch that. Where we proceed to have short replenishment intervals, we can look at those bearings and determine whether or not we can safely extend those bearings to give ourselves the convenience of a little bit more time during this period of time where we're all lacking enough time to get the work done. Lastly, I would offer to you that there is a computer program that's designed to give us the means to put in the details and store the record for the long term if we wish to do so. If you have any interest in understanding the logic behind the radial calculator, or would like to know more about the computer program, the Excel application, please email me, mike.johnson@amory.com, and put Lube Coach in the subject line, and somebody from my company will be back in touch with you. Or alternately, you can click on the link to the left side of your screen and put such a request in the information section there on that link. So the value of optimizing lubrication frequency, there's good reasons to go through this exercise. Grease-fed machines, we can optimize the labor requirements. In this point in time, we just don't have enough labor. So anything we can do to safely push out intervals is a good thing for us. Secondly, we can validate that the products that we have selected are an appropriate fit from having done multiple exercises where we analyze customers' work practices and their written literature about what they need for their techs to provide for the machines. We see time and again that we have a difficulty making the right grease-based decisions for operating machines. This is a very important piece of the exercise. And then lastly, being quantitative about this approach, including calculating the volume, allows us to prevent overfeeding grease to bearings. And I don't know whether you know it or not, but too much grease can be just as much of a problem for your grease lubricated components as too little grease. As it relates to oil-fed machines, this safely stretching those intervals out 0.5 to or once or twice what our current state is gives us the means to optimize labor requirements. That allows us, with our lightened available work staff, to prevent catastrophic failure on oil lubricated components. Then I would offer this, and I'm going to go through this fairly quickly. It is very, very useful to validate our lubrication practices using ultra-high frequency energy analysis, particularly for electric motors and any other bearings that are grease lubricated that are operating in a steady state. This ultrasound is a very high frequency signal, well above human range, 20 kilohertz to 100 kilohertz range. It's difficult to identify because it's a very low sound wave that dissipates very quickly as is produced and can be easily detected by mechanical and electronic equipment. And with that in mind, what we're actually trying to listen for is the moment that there's contact between two surfaces. If I drop the steel ball on the steel plate, it creates a compression wave that propagates through the steel plate. We can pick up the presence of that wave if our sensor is plugged into the right spot. This is ultrasonic energy, and it's a very useful tool for identifying asperity contact that occurs when our lubricant film has failed. This differs from vibration analysis that would be more closely looking for displacement that occurs after the steel ball hits the steel plate. Within our operating machines, what we are looking for, the yellow space here represents the oil film between the machine's working parts. We're looking to maintain enough coverage to keep all of these high spots separate. If we have the wrong grease in place or the wrong interval in place or the wrong volume in place, we can often find ourselves with lots of metal rubbing between the race and the element due to lost oil film. If we are measuring in the right location with the right technique, we can see very clearly what's happening. The data collection side of ultrasonic energy measurement is particularly important. Here's a chart that shows the relative sensitivity for high frequency energy for 6 different kinds of sensor placements. Grease gun mounted transducer is not a highly sensitive, it would be similar to the use of the probe tip. It's not adequately sensitive for high frequency energy measurement. Contact probe is noted here, scenario 1. This gives us this degree of sensitivity. 2-pole magnet is better. Adhesive mounting pads actually getting pretty good. That's scenario number 4. Stud mounted transducers obviously is the best option, maximum sensitivity for collecting high frequency energy. So be careful with data collection if you're going to use this technique. And keep in mind, good ultrasonic practice is all about location, location, location. We need to get our sensor in the right spot in order to know that we are in fact listening to changing machine conditions. Well, that was a little bit about optimizing service intervals for our machines. Let's think for just a second about what we need to do when putting machines into an idle state, whether it's for just a couple days or a couple weeks or several years. Assuming that you cannot turn the machines on and run them for a very short period of time, a few minutes a day, which really truly would be the best practice, we have to consider grease-based components and oil-based components and their respective reservoirs and what needs to be done to protect those components from atmospheric and possibly in-plant process corrosion while those machines' parts are sitting idle. If it's a grease-based component and we know we're going to idle a machine, we should feed the machine according to the standard grease supply practices as the machine is getting ready to go into idle state. We want to have fresh grease dispersed around the races and elements. And as soon as we do that, then we shut the machine down, and that's a relatively healthy state. There are corrosion inhibitors within the grease that will protect races and elements. And that's fairly easy. Oil-based components, a little bit more detailed. The best practice for an oil-based reservoir and exposed machine surfaces would be to apply a oil mist application using a vapor phase corrosion inhibitor or a misting product. Now, this is a little bit impractical in our current scenario. Our idle state may be for a few days or a few weeks or maybe even a few months. And then we're back up and running again. We need the surfaces to be protected during that time, but we don't really have the means to install and possibly even the money to buy. So we could install mist systems on individual machines. It's not a practical scenario. If we do have mist and can continue to feed mist to those machines when they're idle, that's fantastic. Those machines can be turned on and operated for a few minutes with mist in place without any real risk of long-term destruction. Option number 2, a pretty good practice, would be to incorporate the use of a vapor phase corrosion inhibitor. Vapor phase corrosion inhibitor, referred to as VCI. The vapor phase inhibitor is a material that's placed in the bottom of the sump that becomes a vapor rapidly filling the space and coating all of the surfaces that are housed within that sump. Sump surfaces, bearing, gear, race, seal, and other surfaces as well. The sump should be first drained of oil. The inhibitor would be selected and then applied periodically. And I would recommend, well, first of all, follow the OEM's guidelines for your VCI, but recommend replenishing somewhere between 6-month and 1-year interval based upon the provider's instructions. The machine should not be operated intermittently with the vapor phase inhibitor. If we can manually turn the shafts, that's great. But if all we have in the machine is a vapor phase inhibitor, there's some risk to turning that machine on and letting it operate for even a very short period of time. The third option, which may or may not be practical, just depending upon your circumstances, would be to fill the sump completely with oil so that all of the surfaces, all of the rotating machine parts within that sump are underneath the oil level. Now, there is risk of substantial leakage to the shaft stub points for any housing where we do this. The machines cannot be operated when they are full of oil. They cannot be turned over by the electric motor. We could turn them over very slowly by hand or with a shaft rotation device. And that would be acceptable, but we couldn't punch the start button and let it run for a couple of minutes if it's full of oil. Then lastly, this provides moderate protection. If we're going to do this, we should use rust and oxidation inhibited or turbine oil, turbine type of oil, to take that approach. The vapor phase corrosion inhibitors were pioneered in the 1940s. Some types are considered to be hazardous chemical compounds. The first use was around machines that were being shipped around the world related to the war effort back in those days. Volatile corrosion inhibitors prevent corrosion by vaporizing at room temperature and forming a protective microscopic layer on the metal surfaces. There's lots of product brand options on the market. I would strongly encourage you to start with your lubricant provider and see if they have one in their product line that is, per their expectation, compatible with their lubricants, so that you do not have to remove the VCI at the point in time that you're ready to put the machine back into service. A word of caution around VCIs. There are some metals that are sensitive and possibly may corrode more vigorously with the use of VCIs in place. Metals containing that are zinc plate or contain cadmium, zinc-based alloys, magnesium-based alloys, lead-based alloys, other metals that are used for soldering or brazing, we would want to be very careful and very selective about picking a VCI for any assemblies with those kinds of metals. And once again, I would point you back to your lubricant manufacturer and ask them to provide advice from their product line to the product they feel is the best fit for your needs. So let's steps to the use of vapor phase inhibitors. Drain as much of the oil as you can from the machine sump. Apply the volume according to the provider's recommendations that's necessary to fill the cavity space of the machine sump. Periodically turn the rotating assembly by hand if it's possible. And if we are able to turn it by hand, we should rotate it a full 450 degrees, and it should be done at no less than every 3 months while the machine is in an idle state. And then lastly, as I've said previously, we should plan to resupply the VCI about on a 6-month interval. I would encourage you not to go beyond 1 year, whichever kind of product that you choose to use. So that's a little bit of information about putting machines into either short-term or perhaps even long-term storage if it's needed during this period of manufacturing and productivity disruption. Lastly, while many of us anyway, are sitting and thinking about things that are going on, we should spend some time thinking about the kinds of things that can be done quickly, inexpensively, and with substantial long-term benefit with our lubricating oils to support mechanical reliability. I want to talk lastly about low-cost options for lubricant storage improvement. New packaged lubricants are typically considered to be inadequately clean for long-term reliability for our machines. The sources of corruption, the solid particulate that we find inside our lubricating oils, the shipping process, loading and offloading, the shipping containers themselves, material that might occur from lubricant manufacturing within the manufacturing plant itself, and then even the raw materials used to create the lubricant all contribute to the potential for increased contaminant load. A study conducted of roughly 145 lubricant distributors throughout North America, 6 containers at each site, samples taken from 6 of the containers, totes, drums, kegs, pails, 5 different product types in each location with the average of their particle counts summarized here. And from that, we see 2018-14 was the big picture average contaminant load. We know that our critical machines need to be 2 or 3 ISO contaminant grades lower than that in order to provide the kind of long-term protection the lubricant must provide to protect mechanical reliability. So from the starting point, we have solid particulate that could lead to destruction. How do we go about managing that? There are lots of options that we are all familiar with related to the storage of large containers of oil. Polymeric containers like we see here, steel containers, and a different version for steel containers from Descase, Trico Corporation, OilSafe Corporation. All of these are very viable, excellent options even. Each one provides, if the spec for the sourcing is done properly, provides that the lubricants stored within the containers are all filtered when they're being loaded to the container and filtered when they're coming out of the container. That's all very good. That's excellent benefit. There aren't so many options available for the handling, cleaning, storage, and management of drums, kegs, and pails. So I would offer a low-cost option like you see here, that the key to success for whatever approach you take is the element quality, the filter element quality. This example of a drum management station gives us the means to stage a drum or a pail or a keg-sized container, siphon oil out of the drum through the filters, back into the drum, and then when we are ready to put the oil into the container, we can even secure containers with fluid couplers, ISO-B couplers, pump the oil right into the container and maintain a closed loop, high quality lubricant transport mechanism so that the product is conducted in a very clean and safe manner from the point of storage all the way out to the machine. The drum management station is very low cost. It will accommodate any of the smaller container sizes. Units can be wall mounted. There is a base underneath the container for oil retention if there's any leakage or spillage. Each drum stand allows for circulation of the fluid in the drum. Each stand allows for transfer to a closed container, and it's a low-cost option. Now, there's with very little engineering time, you have the means to put this kind of thing together for yourself. But there are vendors that provide this kind of equipment. We strongly encourage you to take a look, see what's available from your filtration supplier organizations. So it's 10:40. That was a fairly brisk run through several slides. I thank you for your participation. If you have an interest in any more details related to any of these topics, I welcome your email, or once again, click on the link to the shared notes there on the side of your screen.
Thank you very much, Michael. I certainly do appreciate that, and I'm sure that the many hundreds of folks that have witnessed this also appreciate it as well. I tell you what, we're going to look to dive deeper into the whole idea of grease and grease analysis tomorrow, and then on Wednesday, and that's going to be with Rich Warsbach of MRG, and then on Wednesday, Matt Spurlock will go into details on condition monitoring, both using inline types of techniques. Thursday, we'll talk about how to pull it all together and drive content mastery. And on Friday, we'll have a roundtable where the four of us get into it and try to figure out what's going on all week. So sure do appreciate y'all sticking around. Please tune in tomorrow, same bat time, same bat channel, for Rich's discussion on grease and grease analysis. And then again on Wednesday for Matt's discussion on inline condition monitoring. And if you're up for it, please stick around on Thursday and we'll talk a little bit about developing competency. Thanks a lot. Feel free to contact us at will.
Thank you, Mike. I appreciate it.